So we're in Unit 2. We are getting towards the end of the unit. Study the 4 example problems that we've just done. It will help you work the others. These 4 different examples can be applied to almost any other situation that's presented in problems. So your first situation, an object starting from rest. The first situation of an object starting from rest was free fall, where we are talking about a dropped object. You can have acceleration from rest that is not free fall. Some examples would be a car accelerating from rest or a rocket accelerating off of the pad. Both of these would start at rest, but they are not free fall. They would have a different acceleration, different from the acceleration due to gravity that we experience in free fall. Second type was an object not starting from rest. Again, it could be free fall. It could be an object that is thrown down. We had an example where a person was on top of a building and threw the ball downward with an initial velocity. Or it could be an instance of an object thrown upward. This is still a free fall situation. It just has an initial positive or upward velocity. With an object not starting from rest, we could have the situation of not free fall. For instance, the ball that rolls up and down a ramp. It did not start at rest. It had to have an initial velocity to roll up the ramp. And it was not free fall. It is not accelerating at negative 10 meters per second squared or negative 9.8 meters per second squared. It has its own acceleration that we have to calculate using the initial velocity, final velocity, time, all of those factors. Another possibility of an object not starting from rest and not free fall is a car or rocket that is accelerating. This might be a situation where a car is maybe driving 30 miles per hour and they come to the edge of town and then they push the accelerator and they accelerate to 50 miles per hour. It is not free fall because the acceleration is not gravity here, and they were not starting from rest because they had an initial velocity. We've covered most of the basics of Unit 2. Now we'll have to add some special cases and some math notes that will help with problem solving. So a special case, an object decelerating uniformly coming to rest. In the stroke picture below, it describes a train accelerating from rest, headed east, or it could represent a train decelerating to rest that is heading west. Which one is it? It could be either one. So this is a shortcut that we can use to help make some problems easier. If an object is coming to rest, we can turn the problem around and solve it as if it was starting from rest. So we are pretending like it is accelerating from rest rather than decelerating to rest. So example 1, a train slows at acceleration of negative 1.5 meters per second squared to a full stop in a time of 30 seconds. How far does the train travel while stopping? We have a handful of options for formulas. This is the formula that will relate distance with time. We are going to rethink this problem. So the train is slowing down, it has an initial velocity, and we know the final velocity is 0. But we're going to change things up, and we're going to pretend that it is starting from rest and reaching its final speed in a time of 30 seconds. So we are going to use the formula that starts from rest. Distance equals 1/2 at squared. So distance equals 1/2 times the acceleration. When the train was slowing down, it was going to be negative 1.5 meters per second squared. If we're going to turn this problem around and pretend like it is now starting from rest, we're going to have to change the sign here. So this will be positive 1.5 meters per second squared. The time is 30 seconds, and don't forget to square the time. That is the number one error when working problems with the distance versus time formula. Distance equals 1/2 at squared. Forgetting to square the time. So our distance equals 675 meters. So this says that if we started from rest, accelerating at 1.5 meters per second squared for 30 seconds, we would have traveled 675 meters. The actual question started at our final velocity, it started at speed and we came to 0, but the acceleration was the negative version of this. It was still 30 seconds. This is the distance that the train would have traveled to stop. A car traveling at a speed of 50 miles per hour skids into the median and stops in 4 seconds. And this question should say what is the distance the car traveled? Yeah. So we're looking for distance. So you can do a couple of different methods here. This is usually our method 2. And you could ask yourself, can I use this formula in this situation? And the answer is yes. So remember how this one works. Distance, the average rate is the 2 speeds added up. So the initial velocity plus the final velocity divided by 2. Times 4 seconds. So the distance, we have our average rate, which would be 25 miles per hour, and a time of 4 seconds, which would be 100 miles per hour times seconds. And this is an odd unit. We're going to change this to make it into something that makes a little bit more sense. So 100, here's our units. So we are going to change this into terms of meters. So we have to do a couple of things here. 1 hour is 3,600 seconds. Hours will cancel, seconds will cancel. So we have miles here. And let's put it in terms of meters. 1 mile is 1,609, to be accurate, meters. And so we enter this in the calculator and we find that this car traveled a distance of 44.7 meters as it skidded to a stop over 4 seconds. This section is a bit of a math review. It is more for helping with your problem solving skills, not directly tested in this class. So it's more of a helpful hint than it is something that's a requirement here. Physics and chemistry formulas are real examples of what we study in math class as variation problems. In Unit 2, we've been using a new type of variation in our free fall problems. First, a review. A relationship that is written y equals kx or a equals kb is a direct variation. We say that y varies directly with x. Some books write it y is directly proportional to x. And this symbol here is a lowercase alpha, the Greek letter for a. And we would say that y is directly proportional to x. This relationship means that as x doubles, y doubles. As x triples, y triples. As x is cut in half, y is halved. The physics formula, distance equals average velocity times time, is a direct variation between time and distance. As long as the average speed is constant. If time doubles, the distance doubles. The next type, a relationship that is written y equals k divided by x, or a equals k divided by b, is an inverse variation. We say that y varies inversely with x. Some books will write y alpha 1 over x and say that y is inversely proportional to x. This relationship means that as x doubles, y is halved. As x triples, y is 1/3 as great. As x is cut in half, y is doubled. It's harder to come up with a physics example for this one. Let's just solve the formula above for t and say that distance is constant. We're going to run a bunch of 100-meter sprints. The formula, time equals distance divided by average velocity. If the distance is constant, if the average speed doubles, time is halved. If the average velocity is 1/3 as great, the time is 3 times as great.